receptors structure, then you have to go with the structure based drug design. If you know only the ligands structure, then you have to go with the ligand based drug design. Okay, in structure like structure based drug design, you can take any target, EGFR or ER, like HERG, any target you can take, and you can screen with thousands of molecules. You can take FDA approved drugs. Till now there are more than 3000 FDA approved drugs are there in the market. So simply you can take all 3000 drugs from FDA approved drugs, and you can dock with any of one of your interest protein. So you will be having some best molecule that can be act for like given for this particular disease also. In structure based drug design, de novo drug design, molecular docking, mmgbsa, molecular dynamic and network pharmacology, and ligand based drug design, pharmacophore modeling, virtual screening, qsar, ligand designer and admet. Okay, so in structure based drug design, as I told you, we are designing a drug by using structure of a particular protein. Do all of you know the structure of a protein? How it will look like? Amino acids. Okay, a sequence of amino acids are protein. Okay, protein is made up of sequence of amino acids, right? So it will be like a sequence of amino acid. If you take a chain in your hand, how it will look? Like that only your protein will be there in your body. Okay, so for example, you can take a pen. Okay, so this is your protein. Okay, in the protein you need a cap on the top of the pen, right? So you need a cap that should be in a particular place. Likewise, in the protein, the ligand should be go and bind to a particular binding packet. Your protein will be having a binding packet. In that binding packet only your ligand should go and bind. Okay, so you have to design a molecule which is going and binding with the binding packet. So if you have no idea from where to take the molecules, and you have no idea about any databases, and if you want to design a proper ligand to target a particular protein, the best method is de novo drug design. De novo drug design is like we are designing a new molecule from scratch. Okay, so you are having a protein. In that protein, binding packet will be there. Inside binding packet, drug should come and bind. That is the concept. So binding packet will be there. We will analyze the binding packet shape, size and volume. How much volume is there, what is the interaction, like electrostatic interactions inside the binding packet, everything we will analyze. Then we will design some fragments. Okay, so there will be a binding packet. Inside binding packet, in this place I can place one hydrogen bond acceptor, in this place I can place one aromatic ring, and in another place I can place one ionic region or hydrogen bond donor group, something like that. If you think in your mind, so you can think in your mind, based on the binding packet's requirement, it will design the de novo drug design process itself. It will design. So this will be your binding packet. Inside binding packet, here one functional group like aromatic should be there, in another place acceptor should be there, in another place donor should be there. Means it will design 3 fragments. It will tell you these 3 fragments, if it is there in these position, the drug will be more effective. It will give you an idea. After that, it will only give you an idea of how to connect these fragments. That also it will connect. At last it will give you a proper drug. So if you synthesize this particular drug, it will perfectly fit into the binding packet of a particular protein. It will give you. Okay, so designing of a new molecule from scratch is called as de novo drug design, right? But in de novo drug design, there is a problem that after designing the drug molecule, synthesizing that particular molecule will be little tough. Why? Because that particular molecule will not be available anywhere in the world. You have to synthesize that particular molecule by your own. You have to design the synthetic scheme for that molecule also. Recently we have done a we designed a new drug molecule by using de novo drug design, and that molecule was not purchasable or synthesizable also. And again, now we are repeating the same process of designing new drug for the same target. Why? Because synthetic visibility. That's the one of the drawback in de novo drug design, and we are doing that de novo docking. Okay. How many of you know what is meant by molecular docking? How many of you used docking softwares or molecular docking? Molecular docking is like you can consider the protein as a key. You can take consider as ligand as a key and protein as a lock. So how the key is perfectly fitting into the lock, if the key is well fit into the lock, then only the key will open, right? Same like the ligands, how much it is fitting into the particular target protein, based on that only it will be like the docking score will be monitored. Okay. So docking is predicting optimal binding pose and affinity of a ligand to target protein. Okay, so docking is purely identifying the binding affinity between the ligand and the protein's binding packet. So you are taking a particular protein, and inside protein you have a binding packet. In the binding packet you are keeping your ligand. You design the ligand by using de novo drug design, right? So how this drug is acting in your body, that is like how two magnets are acting. Right, if you are keeping two magnets near, it is attracting to each other, right? Same like electrostatic interaction will be there between your protein and the ligands. So you will be having a protein, inside protein binding packet is there, inside binding packet you are keeping your molecule. Why? How it is acting? If you keep your molecule just like that, it won't act. It should have an interaction with the binding packet. So that interaction is called as electrostatic interaction. Those electrostatic interactions will be measured and it will give a score, that is called as docking score. Okay, so this docking will happen based on search algorithm and scoring function. Okay, search algorithm is ligand's orientation inside binding packet, in which orientation ligand is there, then ligand's position and ligand's conformation. So inside binding packet, which orientation is having more binding, which position and which conformation is having more interaction, it will find it out. After that, search function, scoring function. Scoring function is nothing but, if you are keeping two magnets nearby, the interaction field will be there, no, the attraction field will be there. That attraction field we will measure. So in docking there will be several types of interactions will be there: electrostatic interaction, van der Waals interaction, hydrogen bonding interaction, hydrophobic interactions. So in docking we are docking score is based on search algorithm and scoring function. Okay, so scoring function is based on hydrogen bonding interaction, hydrophobic interaction, like that. There will be different types of interaction between your ligand and protein. Okay, so between this ligand and protein, what type of interaction is there, based on it will give you a score. So that score is called as docking score, and followed by docking we will do mmgb and mmpbsa. mmgbsa is molecular mechanics, generalized bond surface area, and mmpbsa is molecular mechanics, position boltzmann surface area. These two are nothing but validation of docking. Validation of docking in the sense, in docking between your ligand and protein there is a interaction that you know. For that we have a score, cumulative score. But in mmgbsa, what type of interaction, and for each type of interaction you will be having a separate score. So like coulombic interaction, covalent interaction, hydrophobic interaction, hydrogen bonding interaction, lipophilic, van der Waals, these are the different types of interaction between your ligand and the protein, and for each interaction it will give you a score. Based on that score you can validate your docking. Okay, so followed by docking we generally do mmgbsa or mmpbsa. Followed by mmpbsa we have to do molecular dynamic simulation. Molecular dynamic simulation is like it represents your full system, body system, like how kind of, how can you say, like docking is taking a photograph. Okay, you are having a protein, inside protein you are having a ligand, you are taking a photo, that frame will come. So that frame we will analyze and we will say this docking is good or bad. Same in mmgbsa also, but in dynamics we are taking a video. Okay, so in molecular dynamics what happens is, as I like in that video it is shown, right, that golden color is your ligand and the gray color is the protein. How the ligand is going and binding with your protein we can analyze virtually. So while doing docking studies, you will keep your protein and ligand as rigid. It will not move. Just you will keep your protein and you will keep your ligand, whether it is interacting or not, you will check. But in molecular dynamics, you will keep your protein and you will keep your ligand. You will leave it for a period of time, 100 nanoseconds or 1000 nanoseconds. So after 10 nanoseconds, what is happening? The ligand is near to the protein or it is detaching from the protein. If it is detaching from the protein, the stability will be less. So if you are keeping a two magnet near, then only is there, like same environment we will create in the computer tool using we used to use Schrodinger suit Desmond. So in that we will generate our body system, same kind of environment. Inside that we will keep our protein and ligand complex and we will leave it for a period of time, 100 nanoseconds or 200 nanoseconds. We will take a video. In that video we will get a result like this, how the drug is going and binding with the protein, and after some time it is stable or not inside the protein. Okay, we will come to know by using molecular dynamic simulation. For doing molecular dynamic simulation there are so many softwares. In that, one of the major software which we are using is Schrodinger suit Desmond, and GROMAX is the freely available molecular dynamics module, but you need to know some languages to access GROMAX. So if you know some any Python or some language, you can use GROMAX for molecular dynamics, and there are so many other tools also, Google Colab, PyMol, for molecular docking. And followed by molecular docking, network pharmacology. Network pharmacology is like network pharmacology is like mapping the drug target interaction. Okay, so I told you how to like select a target, right? So in a drug discovery process I told you we need to have a disease in our mind and proper target. Target identification is very important in drug discovery process. In that, to identify a proper target we can use network pharmacology. In network pharmacology what we will do, these color dots are different targets. Okay, so for example, for one disease if you are having 50 targets, you will take all the targets and you will do network pharmacology. In network pharmacology it will tell you which target is more potential by doing creating some networks. Okay, these dots are considered as nodes and the lines are considered as edge. So these dots are different dots are different targets. So these lines are it says that these particular two targets are connected, interconnected. How much the bit the distance between two targets, if it is very close, the targets are very interactive, and it is more effective. So the number of nodes and edges plays a major role in network pharmacology. In that, degree, betweenness, closeness, these are the, based on these parameters only we will select a best target. Okay, so degree is nothing but these particular targets are called as degree. Betweenness is how many bands are there. For example, if you take any one target, that particular target may connect with different 5 targets. So in this, here we have almost 10 targets, right? In this 10 targets, 9 targets are having connection with different 4 targets. Okay, so 10th target is connecting with remaining 8 targets, means that particular target is connected with 8 different proteins, so that is more potential. Why? Because remaining targets are having 4 connections only, one target is having 8 connections. So if you target that particular protein, it will regulate remaining 8 proteins also. So by targeting one target, you can regulate 8 different proteins. So to identify like that potential targets, we can use network pharmacology, and for that we have so many freely available softwares. Network pharmacology we used to do in freely available softwares. One of the major software is Cytoscape and string and streets. These are to generate this kind of network only. Analyzing this network, we can do it in Cytoscape only. Okay, so followed by network pharmacology. So now we are entering into ligand based drug design approach. So till now, what are the drug design approaches we have seen is purely structure based drug design. So if you have a structure of a protein, you can design, or you can what to say, design a drug for that particular protein, or screen a particular drug for that protein. But now we are entering into second phase, which is ligand based drug design. We are using only ligands to design the drugs. Okay, in that first one is pharmacophore modeling. In pharmacophore modeling, we are like what we are doing is, as I told you, if you are having a 20 or 30 number of molecules, but you don't know the target protein. Okay, so what you can do, you can take all the 20 molecules, you can analyze all the 20 molecules structure, pharmacophoric feature, what are the pharmacophoric features are there in the different molecules. Like if you take one molecule, 2 aromatic rings and 1 acceptor ring is there. So if you take second molecule, 2 aromatic ring, 1 donor region will be there, same acceptor region will not be there. So designing a frame of your drug. Frame of your drug is nothing but, in that if you take any chemical structure, what are the derivatives side. For example, hydroxyl group will be there, NH2 will be there, keto group will be there, those are called as derivatives. The frame is, core molecule is two ring is there and one acceptor is there, that is frame. The core structure, it will analyze all the core structures. If you are giving 20 or 30 set of molecules, means it will analyze all the 20 and 30 set of 20 or 30 molecules, and it will say that this, out of these 20 molecules, 18 molecules are having same features. So like this, for example, in this is acceptor, this is acceptor, and this is donor. Okay, so this is my pharmacophoric hypothesis. I have generated this pharmacophoric hypothesis. What I have done is, I have taken 23 molecules which is there in the market, and I have generated a pharmacophore model. In that, I got this hypothesis, which is having 2 acceptors and 1 donor. This is the length between all 3 features. This is the pharmacophoric feature which I got. So what we can do, after getting this particular pharmacophoric feature, we can do virtual screening. In virtual screening, what we will do, we will take this particular pharmacophoric hypothesis, and we will screen what are all the molecules are having the same pharmacophoric hypothesis. Okay, so if, for example, in this case, I have taken 4 lakh natural compounds from a database called coconut database. From coconut database, what I have done, I have collected 4 lakh natural compounds, and all 4 lakh natural compounds are I have screened with this particular pharmacophoric hypothesis. Out of 4 lakh molecules, 1 lakh 5,000 molecules were having the same pharmacophoric hypothesis. So what I can assume, out of 4 lakh molecules, this 1 lakh 5,000 molecules may act as the target lead molecule for my particular protein. So I have taken all 1,05,000 molecules and I did docking MMGBSA dynamics as we saw before. Expect the designed molecules to bind to the target protein. Then QSAR. QSAR is like correlates evaluation and in vitro studies. You will be having some in your particular structure in seventh position you are having OH group. Because of that solubility is increased, so your drug is having more activity. Or in eighth position you are having amino group, that amino group is increasing the pH, that is not good for the activity. So like that, what are the derivatives are having impact on the biological activity, you will come to know in QSAR. For that also we are having so many modules. We used to do QSAR and Schrodinger suit, that is paid version. 2D QSAR is a free version to do QSAR. In the QSAR also there are so many subtypes. Major subtypes are 2D and 3D QSAR and ligand based drug design. In ligand based drug design is like same like docking. After docking, okay, so you are having a binding packet. Inside binding packet you are having a ligand. In that ligand may clash with your protein. So this is your binding packet. For example, you are having a ligand, that ligand is going and touching the binding packet. You will not know that. Because of that the docking score may be uh, less, or the stability will not be there. So in that case what you can do, you can do a ligand designer that will tell you which portion of your ligand is interacting with your uh, target protein perfectly, and which portion of your ligand is not interacting with your protein, which portion you have to modify. So for example, in this particular, that red color region is showing bad sitting inside the binding packet perfectly, and those red region means those derivatives of that particular region of ligand is going and touching the protein's binding packet. So because of that it will not touch any time, the ligand will not go and touch the protein, it will be having an interaction only. So when it is touching, it will change its conformer and the stability will be reduced. So because of that particular corner only, this molecules stability was very less. So then we designed the molecule and we cut those particular portion, then that particular molecule was showing the better activity. So that we can evaluate using MPV. There is a score which is cumulative score of 5 different parameters, which will evaluate all these parameters and it will give you a score. So based on that you can say that the newly designed molecule is will fit to the binding packet. So what we can do, we can design a molecule